All right, welcome to BIO347, Biostatistics and Experimental Design. I'm Dr. Jeff Stratford from Wilkes University. This is part 2, data variability, in the chapter Exploratory Data Analysis. So what we're going to talk about today, or this moment, is the spread in your data. So the previous lecture was talking about where your blob is. And so now we're going to, and when I say where your blob is, I mean, think about a blob on a number line, okay? So like, where's your average number occurring? Now we're going to talk about the variability, which is how big is your blob. All right, so first thing, easiest measure is the range. So the range is going to be your, so the range is going to be the smallest and largest number. And that's it, okay? Oftentimes, you'll have people subtract the largest from the smallest, and that gives you a range. That's one way to report it, but my preference is you actually give the smallest and largest, because if I say the range in arm length was 7 centimeters, it doesn't give you any sort of scale on there. But if I said the range in arm length was, 120 to 127 centimeters, then it makes that 7, just visualizing what that means, much more easier. More easy. All right, so a residual, okay, is an observation relative to typically what is considered a mean, okay? So if you have a series of numbers, let's say we have, our mean is 5. And if we have a series of numbers, we'll say 5, 5.1, 4.9, 4.8, 5.2, right? Then the residual, right, is going to be the difference between these, okay? So actually, let me put here. So the question is it the mean minus the observation, or the observation minus the mean? Here's how I remember it. If an observation is larger, then it's more positive. And so our number should be more positive. So it's above the mean. If a number is below average, right, it should be negative. So the only way that turns out if you do that is if you do this. Okay, so let's check. So 5 minus 5. So we'll do this. The residual is 0. 5.1 minus 5 would be 0.1. And then 4.9 minus 5 would be negative 0.1 minus 2, and then 0.2. Okay, so here's our residuals right here. Residuals are extremely important when you're thinking about what's happening to create my observations. So what's the process behind creating the observations? Well, you have a mean that's kind of hidden in here, and then you have wiggle about that mean, okay? So, for example, take this observation. Why is this observation above the mean? Okay, what aren't we looking at? What's not accounted for in the mean that makes that observation much larger? And we could look at this one and say, why is this less than the mean? Okay, So we'll come back to residuals as we go through our different tests and we'll interpret them accordingly. All right, the sum of squares would be, so if we look at our residuals, we're going to take our residuals, we're going to square, and then we sum. Okay, so we square each of these, and then we sum it up, and that gives us our sum of squares. Okay, things to consider. The reason why we square is that if you have data that's kind of like this, and you just add it up, it'll be a very small number. So when you have observations, let's put a mean observation here, individual observations like this, right? The residual is this distance, okay? So these will be positive and these will be negative. When you add negatives to positives, right? And you sum them up, they'll cancel each other out, right? So by squaring, you're getting rid of that, that sign and the ability to cancel things out, okay? So, but it is a square number. So if you, like if this is arm length in centimeters, the sums of squares is going to be centimeters squared, okay? All right, residuals, sums of squares, the variance. So the variance is, well, think about this. So if we just took sums of squares, we're adding, right? It's additive. If we have lots of observations, it's going to be some huge number, right? So what the variance is doing is it's balancing and accounting for the number of samples, okay? And so the variance, right, and a theoretical distribution or hypothetical distribution is sigma squared. It's often in a sample called S, right? And what that is, so it's the sum of squares. Okay, divided by n minus 1. So if you're talking about a population estimate, it's just going to be n. If you're dealing with a sample, it's n minus 1. Okay, so that's the variance. The variance is an important number, but not unto itself. So normally we don't report the variance. For one reason, the units are still squared. So if you're measuring something in centimeters, this is going to be centimeters squared. If it's area, right, and it's a centimeter squared, this is going to be centimeters to the 4th. So the dimensions of it are square of the original dimensions. So, okay, how can we get rid of that? So we can look at standard deviation. Standard deviation is sigma, or just S, and that is going to be the square root of the variance. Okay, and so by taking the square root of the square, you get back to your original units. So if you're measuring something in centimeters, okay, the standard deviation is going to be also in centimeters. So think about what this kind of looks like, right? So if we look at the mean, let's just put the mean up here real quick. How do we calculate the mean? We sum the observations and divide by n. So if you look, these two formulas kind of look the same, right? And what I want you to think of is what standard deviation is telling you is it's almost like the average deviation or the average residual, right? Because remember, at the heart of this, right? The heart of this is the residual, okay? And what you're doing is you're dividing by the sample size, okay? And it's n minus 1 because you'll underestimate the variance if you don't do that. And this accounts for degrees of freedom, okay? So that's what this does, okay? So it gives you the average residual on the same scale as what you measured, right? So you can report things like something was 35 plus or minus 12 centimeters. If you report something like this, you should say the average and mean respectively was, and then report this. Otherwise, this could be several different things. All right. So we did variance, standard deviation. Okay. Some things about the standard deviation and what it means. All right. So I have a table in the book. Let's just go over it real quick. A standard deviation, if you just calculate it, that is the one standard deviation unit, okay? And we can look at that in terms of the percent of the data included, okay? And it would be 68.3% of the data is included within standard deviation. First, there's a very special condition, and that condition is that your data are normal, okay? And the reason why that's important is if your data takes on a different shape, right, than a nice normal curve, then this will not hold, okay? So if here's a frequency distribution, right, making that as normal as I can, okay? So here would be your mean. If your data are symmetric, when you do one standard deviation unit, you're grabbing most of the data points, right? 68, right? 68.3% is one standard deviation. If you go out 1.96, that seems like a weird number until you look at the percent, 95%, right? So if you go out 1.96, right? So from here to here is 1.96. Okay. Notice that 95% is important because what's left over is 5%, right? 5% is like that area under a curve, right? Where you have your critical value and more extreme. So 1.96 standard deviations is important to get that marker of 95%. All right. Then 2 standard deviation units gets you 95.5. And then 2.58, another weird number, but that represents 99% of your data. And 3 standard deviations gets you 99.7% of your data, okay? So 3 standard deviations, it's way, way out, okay? Way out here. So just a very small percent of your data, right, is outwards. All right, so standard deviation is good to know because somebody, like I said, know thy data, my first commandment of statistics. I told you the mean, then that gives you an idea, right? So if the mean height of a group of people you meet was 8 feet tall, you'd say, that's really incredible. And if I told you the standard deviation was 3 inches, then you know that everybody's very uniform. If I told you that the average was 8 feet and the standard deviation was 3 feet, that tells you you have some very, very tall people and people that are, 5 feet, so relatively normal. So with those 2 pieces of information, right, the mean and the standard deviation, you get a pretty good idea of what your data looks like, okay? And also what it shouldn't look like. So it's a good way to recognize observations that don't fit, or if you do a calculation of a mean, if you get a bad calculation, should be able to visualize what that means and say, like, something went wrong here. All right. Standard deviation. Oop, I forgot standard error. So standard error is next. Standard error. Okay. Standard error. There's no symbol for it. Often you'll see SE or SEM. Okay. Standard error of the mean, and that's going to equal our standard deviation divided by the square root of n. Okay. So this gets kind of complicated because if we look at what the standard deviation was, right, we have the sum of squares right? And then we divide this by the square root of n. So here's what I want you to think about. The standard deviation, right? We're adding up all the residuals. And if you have a lot of samples, you get some huge number that doesn't count for the number of samples. So you divide by the number of samples and that levels it out. To get the standard error, you're dividing again by the square root of n. So this number is for any particular data set, right? This will be fixed because every time you add something here, you're adding below. Okay. When you look at the error, that happens, but then you're dividing again by the square root of n. So typically what happens is as you get larger and larger samples, your standard error gets smaller and smaller and smaller, okay? Not as, well, I'll leave that for later. But anyway, typically the standard error is smaller than the standard deviation. And it has a different meaning. Standard deviation, when I tell you what standard deviation is, what that means is it gives you the confidence you have in a particular estimate. So standard deviation, when you calculate that, the more samples you have, basically it's going to bounce around and it won't change that much. And what I mean by that is as you add observations to your calculation, okay, it's the standard deviation. So it's giving you the average residual size. So it's going to bounce around, right? What it's not changing, let me put it this way. Since you are trying to figure out the confidence in a measurement, right? This tells you, the standard error tells you how confident you are in a particular parameter. In this case, the standard error, the mean would be the mean, right? So what I mean by that is if I gave you okay, if I give you two standard errors, okay, 2.97 and 10.1. Relative to this mean, right? What this measurement is telling you, 53 plus or minus 2.97, it's saying within a certain confidence, okay, that the mean is essentially, we can just say this is 3, that it's 56 or 50, okay? So given it's 53, 56, and 50, you know, that's pretty good, right? But if our standard error is much larger, then our mean, not the shape of the data, it's not talking about the shape of the data, but our estimate of the mean is falling with the same confidence level between 43 and 63, which is a much larger range. So the standard error is basically telling you how good your measurement is. So that's the mean. You'll also, so for example, if you have a line, you're going to have an intercept, right? And a standard error of your measure of the intercept. You're going to have a slope, right? And you're going to have a standard error associated with the slope, because you want to know, is your relationship really like this, and or is it like this, in which case this is not the best measurement, right? So if your standard error is much tighter, you can say I have a lot of confidence in my slope. But if you have large, right, this is pretty much a flat line, there's a possibility that your actual beta is 0, right? So think about standard errors as confidence in measurement, and your standard error is the variability in your actual observations, right? Not the parameter you're generating from those things. All right. Confidence intervals. So confidence intervals are like standard errors. Okay. So usually what you say is like a 95% confidence interval, right, would be your data. And the way you calculate that is 1.96 times your standard deviation. Oops, we're going to say plus minus. Okay, so all you do is multiply whatever you calculate your standard deviation to be, multiply it times 1.96. Okay, so, and confidence intervals are often portrayed like this. You know what else is portrayed like this? Standard deviation. You know what else is portrayed like this? standard error. So if you see a graph and you see this, or you see this, you have absolutely no idea what this means unless, of course, okay, good graphs, what they should say is, you should get a graph like this. And then I'll say mean, let's say heart rate plus or minus 1.96 standard deviation. And then you're like, oh, okay, I now understand what that means, okay? Or it'll say, here's another common thing you'll see is an estimate, mean heart rate, plus or minus 2 standard errors, okay, which is about 95%, okay, of the, so about 2 standard errors, about 95% of the estimate in the means, okay. So what that means is here's your estimate of the mean, but because you took a sample, the actual mean is somewhere in here. So if the actual mean's up here, right, and the actual mean can be here, it means that these data overlap and these two things may not be different, right? So that's why it's important to know not just what your means are, but also the variability, okay? And always write down or indicate on a graph what your error bars are. Is it standard deviation, standard error, confidence intervals, or something else? Could be the range, right? Oftentimes, if you have small data, you could do things like this. You could have the mean and actually put the observations there. Okay, some people do that. Whatever gets your message across, that's the important thing. All right. Credible intervals are a Bayesian version of confidence intervals. And that's all you need to know. All right. Quantiles. Quantiles, what that means is, well, you know some of these things. One is percentiles, right? Converting your data over to percents. And then there are quartiles. Okay. Percentiles and percentiles and quartiles are handy when you're talking about large numbers. And you just want to know something like, where does a particular observation lie? Is it in the, so quartile would be if you ordered your data, right? So let's say this is just some, you only have one group and you just take a whole bunch of measurements, right? So these can be whatever. Percentile is going to break this up, right? So you have your median, which equals 50. And then your percentile is going to break this up into 100 parts. Right? That's not 100, not even close. But if, let's say these were MCAT scores, and this is U, right? If this is the 99th to 100, then you could say, ooh, I scored in the 99th percentile, right? Quartiles, what it does is instead of breaking up into hundreds, right, all it does is you have the median, but all we're going to do is break this up into fourths. Okay, so this would be the top 50 to 75. I mean, 75 to 100, 50 to 75, 50 to 25, and 25 to 0. Okay. R, when it builds box plots, okay, it's going to do a box that contains 50% of your data. So there you have the median. That's the 75th, the 25th. So you know that 50% of your data lies in here. And then this is something that's pretty close to about 95, the 95th percentile, right? So it's a little bit of a mix of percentiles and quantiles, right? What I haven't talked about in this chapter, it's not listed in the book, is outliers. And outliers, what they are, these are residuals that are outside of some specified range, right? And what a lot of people do is say within 3 standard deviation units, right? So it's the top 99 point whatever percent of your data in the bottom, okay? Less than 1% of your data. And there's just extreme measurements, and then there are true outliers, and we'll talk about that. We'll have a bit of a lecture on outliers. Skewness and kurtosis. Okay. And let me just say that you use percentiles and quartiles, not only when you have big data, but when data are skewed, you can break this up. And just go back to our box plots. You can have box plots. Nope. Get rid of that in a second. Let's just make the point. You can have box plots where the median is not in the center. Okay. And what this is when you have data that are very skewed, right, like this, that'll turn this box plot, we turn it on its side, to be like this. Okay, and you'll have something like this, and let's say this tail goes on and on and on, and then you might have something like that. So what we'll work on is being able to take a box plot and from that visualize the type of distribution. If you're lucky and your data is normal, then your box plot will be nice and symmetrical. Good luck with that. All right. Skewness and kurtosis. So skewness is if we take a normal distribution that's symmetric about the mean and we push it, okay? So we push it this way and we push it that way. And think about the bottom as being sticky, but the top can move. So if we push it this way, you're going to get data that look like this. Okay. If you push it the other way, you'll get data that looks like this. When you do the calculation, you'll get a number, right? An actual number. where skewness here is 0, okay? You get a negative number, right? If your skew points less than the mean. You'll get a positive skew if this extends, if the tail extends in a positive way. And the way I remember this is, I think of this as a skewer. So if you know what a skewer is, you use them at barbecues. So, you know, you can do things like put a mushroom on a skewer. You have a tomato, onion rings, etc. All right. So that's skewness. So that just tells you, you know, which way the wave is going. And what I want you to know is whether something's positive. So when you calculate it, you get a positive number, your number's going to look like this. Negative, it's going to look like this. You can have something wacky like this. But since it's symmetric, it's going to be close to 0. So beware that just getting 0 skewness does not mean you have this beautiful data, right? We got a whole chapter on graphics, and getting to know that data involves a lot of staring at histograms. We just showed these are all what we call histograms, looking at the frequency of outcomes. All right. Kurtosis. So nope. Kurtosis. There we go. Has to do with how flat or how peaky it is, a normal distribution. Right? You can ignore it. It's meso. Curtic. So that meso means middle, right? So it's the middle between two extremes. Okay. So we're going to draw, so this will be some mean. We're going to draw the other extremes. So one extreme will have all your data pile up, okay, with very, very small standard deviation. This is called leptokurtic, okay, where lepto means narrow, okay. So you'll see lepto in ecology when it refers to the range of some environmental variable in which organisms live. So like leptohaline means marine animals that have a very narrow range of salinity they can live on, right? And the same is true for enzyme activity, right? Some enzymes are very, very, very particular about what pH or temperature they work at. All right, so it'll be very peaky. And the other thing is, the other option is very flat. And flat is platykurtic, where platy means flat, like plateau, okay? And one of the weirdest mammals, the platypus, right? Flat mouth. All right, skewness and kurtosis. So we'll create some data distributions and then look at these numbers. All right. Last thing is the coefficient of variation. CV. No, no. Nope. Nope. Boy. So I'm using this thing called a bamboo. Maybe you don't want to get it because it's kind of crap. CV is equal to the standard deviation over the mean. Okay. All right. The reason why you're going to do this is if I told you the standard deviation and want to compare things that are measured on very different scales, the standard deviations aren't meaningful. And what I mean by that is if I said a standard deviation is 27, right? If you're measuring something in the thousands, 27 is not very large. But if you're measuring something, say, within the range of 50 to 100, then 27 is very large. And the way to correct for that, right, to make it relevant is by dividing by the mean. And then you multiply that number times. Looky there. You measure that number times 100, okay? So standard deviation divided by the mean, it scales it, okay? And removes, so here's why you can use it to compare like apples and oranges and variability. So if you want to know like evolution, does it work on, say, let's say you're studying acorns and you want to know, does the height of the acorn, is that more variable than the width or some other attribute? Okay. And the way you can remove and compare apples and oranges and different things, it's because the units go away. So if we're looking at, say, acorns and we're looking at width, it might be measured in millimeters. So the standard deviation is millimeters and the average is millimeters, and those cancel. Okay. So that's the nice thing. It just gives you a number. And now you can look at variability among different systems. Okay. And that's the coefficient of variation. All right. That's it for this chapter. There's more stuff, but we're not going to cover it on correlation and regression. We got a whole chapter on it. I want to get on to data distributions. And with that, I'll close up. If you have any questions, please feel free to send me an email. All right, thanks.